So continuing our finding derivatives of functions, we're going to talk about a powerful rule here called the chain rule. Now, the chain rule, we need that rule to find derivatives of compositions of functions. So for here, we wouldn't need the chain rule to find the derivative of this binomial. But if this binomial was raised to a power, then we actually do need the chain rule. We don't need the chain rule to find the derivative of 3x minus 5, but we would need the chain rule to find the derivative of square root of 3x minus 5, which would actually be the same as 3x minus 5 to the 1/2. So if we had a polynomial, we wouldn't need the chain rule, but if we had that polynomial raised to a power, we would need a chain rule. Or if we had x raised to a power, we wouldn't need the chain rule, but if we had a trig function raised to a power, we would need the chain rule. Now, the other thing we might need the chain rule for is trig functions. So I showed you earlier how to find the derivative of sine of x, but what if instead of sine of x, what if it was sine of some function of x, like x cubed? Then we would need the chain rule. Okay. Basically, the chain rule, the formal definition of the chain rule, says that if y is a composition of two functions f and g, then the derivative of y, where g of x is actually the u, so g of x is actually, we're going to say that's g of x is u. So then the derivative of y with respect to x actually can be written as the derivative of y with respect to u, and then times the derivative of u with respect to x. Now I find it a little bit easier to follow if I write it like this. The derivative of f evaluated at g of x is actually the derivative of f evaluated at g of x times the derivative of the g function. Now, I prefer, over all these definitions, I prefer this one. If we think of the composite function as a function of u, function evaluated at u, where u is g of x, or in other words, u is a function of x, then the derivative of f of u with respect to x is actually the derivative of f evaluated at u times u prime of x. Okay? Now, up to this point, we really only have two rules to build on, the power rule and the trig rules. So you can actually take this chain rule, and instead of having a simple power rule, we can actually come up with a more general power rule. And so let's assume here that we have some function of x to a power. Well, if we have some function of x to a power, like u to the n, well, we can apply the power rule like we did before. It would be n times the function to the n minus 1 power. But then you have to remember to yank the chain. So you have to keep the chain going here by multiplying by u prime, the derivative of the function. Okay? So let me give you a simple example of that. Here I have a function raised to the 7th power. So I'm going to think of this function as u. This trinomial is going to be u. So I have u to the 7th power. Okay? So to take the derivative of that using the general power rule, I would apply the power rule. So I'd bring the 7 down, and then I would have the function raised to the 7 minus 1, which is the 6th power there. So I'd have 7 times the function to the 6th power, and that's the power rule portion. But then the chain rule portion is that I then have to multiply by the derivative of this function on the inside. So I have to multiply by the derivative of this trinomial. And the derivative of this trinomial would be 3x squared minus 6x. Okay. Now, you can also have trig functions involved in this power rule. Now remember, one way to write tangent to the 5th x, let me write it for you. So another way to write tangent 5th x is to just write it as the quantity, the tangent function, the whole quantity of that tangent function raised to the 5th power. Now, So this is like having u to the 5th power. So the derivative of that would be 5 times u to the 4th power. But then remember, you have to multiply by the derivative of u, the derivative of the inside. So we have to multiply that by the derivative of tangent x, which is actually secant squared x. So these two examples are examples of the power rule. Now, another example, though, that we could talk about would be the trig rules. With this chain rule, those trig rules we had earlier I told you the derivative of sine x with respect to x is just cosine x. But what if the argument for these trig function, like what if the argument for the sine is not x? What if it's some function of x, like u? Well, then the derivative of sine u would actually be cosine u times u prime, where u is a function of x. And similarly for other trig rules. So if I wanted to take the derivative of sine u, so here I have the derivative of sine u where u is x cubed. So I'm going to take the derivative of sine of x cubed. So what's the formula say? It says that derivative would be cosine of u, so I would have cosine of x cubed, and then I multiply by the derivative of this argument. So the argument is x cubed, so the derivative of that argument would be, the derivative of x cubed would just be 3x squared. And then you could turn it around, because we usually put the 3x squared to the left of the cosine function. So you could write that as 3x squared times cosine x cubed. Now another example of this would be, here's tangent of, not tangent of x, but tangent of some function of x. So remember, it works just like this. The derivative of tangent x was secant squared x, so the derivative of tangent u would be secant squared u times u prime. So the derivative of tangent u would be secant squared of u, so secant squared of this argument, and then we multiply by the derivative of this argument, and the derivative of x squared plus 3x is simply 2x plus 3. Okay, so I'll do some other examples, and I'm going to speed this up a little bit. You can rewrite this as x squared minus 5x plus 3 to the 1/2 power, and then when you take the derivative, you get 1/2 times x squared minus 5x plus 3 to the negative 1/2. But then you've got to remember to multiply by the derivative of u. So the derivative of the inside would be 2x minus 5. And then you can simplify that as 2x minus 5 over 2 times x squared minus 5x plus 3 to the positive 1/2. This one, I can rewrite this one as 2x cubed plus 11 to the negative 4. And then I can take the derivative using the general power rule. So that would be, bring the negative 4 down, then it would be times 2x cubed plus 11 to the negative 5. And then you multiply by the derivative of 2x cubed plus 11, which is 6x squared. And then since negative 4 times 6x squared is negative 24x squared, you can write that. And then you can move this to the denominator as long as you change the negative 5 to positive 5. Okay, a couple more. Y equals x cubed. That can be written using the power rule. We can take the derivative of that. We get 3 cosine x squared, and then you have to multiply by the derivative of cosine. So you have to multiply by the derivative of cosine, because this is like the cosine quantity cubed. So it's 3 times the cosine quantity squared, and then times the derivative of cosine, which is minus sine x. And then I just put the minus over here. So I got minus 3 times cosine squared x times sine x. And then here's a square root, so you can write this as 3x minus 5 to the 1/2. So apply the general power rule, you get 1/2 times 3x minus 5 to the negative 1/2, and then times the derivative of 3x minus 5, which is 3. And then finally, your 3 goes in your numerator, and then the 2 goes in the denominator. And if you move this to the denominator, you'd have 3x minus 5 to the 1/2, or just the square root of 3x minus 5 in the denominator. One way to think of these derivatives involving the power rule here is just that this is the inside and the power is the outside. So you take the derivative of the outside, so you apply the power rule 10 times this function to the 9th, and that's the derivative of the outside. And then you multiply by the derivative of the inside, which would be the derivative of this. And the derivative of this is 12x squared minus 14x plus 2. And then another example here, this one this one is not a power rule, this is a trig rule. So in this one I would think, okay, the derivative of the outside would be the derivative of the secant. So the derivative of the secant, so I would apply that first. So the derivative of secant u would be secant u tangent u. So I'd have secant x cubed tangent x cubed. Then I would multiply by the derivative of the inside here. In other words, the derivative of the argument, which is actually the derivative of x cubed, is 3x squared. So the derivative would be 3x squared times the secant of x cubed times the tangent of x cubed. So this can be a little tricky when you get to these trig rules. So just remember, there's a difference between having the secant of x to the third power and having the secant of where the argument is x to the third power. Okay, I'll finish this with some nested chain rules. So here I have sine of the argument 2x to the fifth minus 7x, and all that's to the 8th power. Well, that's the same as taking that whole sine function and saying it's to the 8th power. So the first thing I'm going to do is the general power rule. So the general power rule, I would say 8 times that sine function to the 7th power, but then I'd have to multiply by the derivative of that sine function. And the derivative of this sine function, the derivative of sine u would actually be cosine of u, but then I'd have to multiply by the derivative of the inside here. So multiply by the derivative of 2x to the fifth minus 7x, which is just 10x to the fourth minus 7. So finally I end up with 8 times the sine of the argument to the 7th power, then times the cosine of that same argument, and then times the 10x to the fourth minus 7. And so it can get kind of nasty when you have those nested chain rules. Okay, and here's one. I actually have to use the product rule for this one. So I have x squared minus 3 to the fifth and 2x minus 3 to the fourth. Now I'm going to treat the x squared minus 3 to the fifth power as u, and I'm going to treat the 2x minus 3 to the fourth power as v. So I would take u, which is this thing raised to the fifth power, times the derivative of v. Now remember, to take the derivative of this to the fourth power, you have to apply the general power rule. So we'd have 4 times 2x minus 3 cubed. Then we have to multiply by the derivative of the inside. So the derivative of 2x minus 3 is 2. Now the next term, I'm going to take v, so here's v, and then I'm going to multiply times the derivative of u, which would be the derivative of x squared minus 3 to the fifth. The derivative of x squared minus 3 to the fifth would be 5 times x squared minus 3 to the fourth, but then I have to multiply by the derivative of the inside, the derivative of x squared minus 3, which is 2x. Now the rest of this is just cleaning up the algebra. So what I did here is I noticed that if you look at these two terms, there's two terms here. Okay, so there's a term, and then here's a term. And if you'll notice, that first term has a common factor of x. This has a factor of x squared minus 3 to the fifth. This has a factor of x squared minus 3 to the fourth. So I can factor x squared minus 3 to the fourth out of those two terms. And then here, this has a factor of 2x minus 3 cubed, and this has a factor of 2x minus 3 fourth. So I can factor a 2x minus 3 cubed out of both terms. Now, when I factor these two expressions out of this term, I'm just going to get x squared minus 3 times 8. And then when I factor it out of this term, I'm just going to get 2x minus 3 times 10x. And then I can clean up what's inside here, and that turns out to be a trinomial, 28x squared minus 30x minus 24. And then I just bring these other factors down that I factored out. I did one last thing. I factored a 2 out of the trinomial, and I put it over here, and that just cut these terms that's in the trinomial in half. So it gave me 14x squared minus 15x minus 12. So my factors are 2 times x squared minus 3 to the fourth times 2x minus 3 quantity cubed, and then times 14x squared minus 15x minus 12. So that's the derivative of that expression. And if I needed to set it equal to 0 to find the zeros, now I could. In the next video, I'm going to talk about higher order derivatives, like the second and third derivatives.